Hello, good morning to all of you. Let us start the class. Uh, this attendance is very poor. 7 people, I think 7 people, but they have to make a balance with your exams and classes because in this semester, I don't know, we'll have enough time to. If we don't teach now, we may not have enough time to cover substantial material. Anyhow, those who are not attending, please send message. They will not able to follow this course at all because all these are very essential. So competitive exams are important, but at the same time, if you don't attend the classes, without attending classes, no point of qualifying also, because that will you'll suffer for that. So you have to keep a balance between this. Anyhow, so let me know if you have any queries, questions regarding last lecture. Last lecture we have started. Okay, so I am not going to review much, but uh, we arrive at that operator u t1 x1 t2 x2 is in Heisenberg picture. It is the inner product between the state vectors, basis state vectors. So that will be using to calculate this. But that was the last I mentioned how it comes in Heisenberg picture. But this another important thing which you generally don't pay much attention to your quantum mechanics courses is the operator ordering, and I found there are questions on operator ordering. So what is the meaning of operator ordering? When we go from classical mechanics to quantum mechanics, we know that these dynamical variables xp in classical mechanics will be operators x and p. Now, classical mechanics, your xp is same as px. So no, because they are some function variables. So this there is they are not operators. So their order is not important. But if I write the corresponding to this Hamiltonian, then it will be my x p Hamiltonian. If I write this Hamiltonian corresponding to this classical operator, it will be p and x. But quantum mechanically, they are not equal because we know x p commutator is ih cut. So they are not equal. So classically, I have suppose a system xp. I quantum mechanically whether I'll write this one or this one, there is ambiguity. So we need a some convention to order the operators. Okay. So that is why this operator ordering comes. So there are few here. No physics can tell you. You have to make a convention. Convention like in India we drive car in the left hand side. In Europe, America they drive car in the right hand side of the road. So this is the convention. So we have to make convention or different and there are different convention. For example, there is convention of uh, normal ordering. One of them is called normal ordering. Okay, so normal ordering means that if you have let me write example so it will be clear to you. So normal ordering means if you have xp, then if you normal ordering I write no, so it will be always p x. P always should be left of x. For example, if I have an operator x p x in or x square x square p or x square p operator or x p x operator or p x square operator in the classical mechanics, all this will be normal order to momentum will come first, so p x square. Okay, so this is the meaning of normal ordering. So if you have a normal ordering, then your p always will be sit left of this. This is a convention. This is not coming from any physical requirements. Okay, then but this is not some people can argue that why p should be in the left, why not x. So this is of course a ordering, but it is not very popular ordering. So there is another ordering which is called while ordering, and this is better in the sense this is much more democratic, that they don't pay any biasness to p or x. For example, xp, this while ordering it will be xp plus px, so both possibilities and divided by the number of possibilities. So this is while ordering. Similarly, if you have like this x p x or this any of them, and then if you make a while ordering, so it will be all possible structure. For example, it can have a x square p, it can have x p square, x p x, it can have p x square, p x square. So all these possibilities, and then there are three possibilities, so 1/3. Okay, so this is the ordering problem, and when you do quantum mechanics properly, you have to consider this ordering from classical to quantum. When you do this, if you either you have to check normal ordering or you have to take while ordering, or okay, this is good enough for you. There may be other ordering, or so we'll follow this while ordering and we'll see that what is the consequence of this. I'll show you both. For example, if I have a, suppose I want to take a inner product of x prime state Schrodinger picture and Hamiltonian in normal order. Normal order also you were came across in last semester when you have to remove the infinite ground state energy. Normal ordering, by normal ordering you remove the infinite ground state energy. Okay, so this let me tell you that what is the if you do the normal ordering, then what will happen to this, and what will happen if you do the while ordering. So that both will discuss. So I can insert this equation. I can write as this xp, and I want to insert a the completeness relation in the momentum basis. So after h normal ordering, then I'll put the pp. This is the dp pp will give you the 1 unity, and then I have the x. Okay, this I can always do. What I have done, I have inserted this times this integration, which is unity, that we know this is the completeness in mom. But why I do like this? Because when I write normal order of this, uh, just a moment, there is some confusion. Let me check from Ashok Das book. I think the argument here may not be valid, which I'm going to tell you, but just do it. While ordering is fine, but normal ordering, okay. So everything is fine. What I wanted to do, I wanted to instead of putting it here, I need to put in appropriate place. No, so actually I need to put this here. So dp, let me write again. So this is not, of course this is correct, but it is not helpful. So x prime, then I put p times h normal order times x. It will be clear in a moment why I put like this. See, now h normal order. So whatever function h we have, momentum will be in the left, right? Normal ordering means momentum in the left. So if momentum in the left, it can act on this p state. So that is the whole idea of this. So momentum in the left, so it can act on this, and then this p is function, x is function of x and p. So momentum on the left, so it can act. So you will have, and this factor we know, and x on the right. So in the normal ordering, x will be on the right. So I can replace the operator x p as that. This will be replaced by h normal ordering xp with the simple its eigenvalues, because now this operator is arranged in such a way that in the left momentum operator which can act here, in the right we have x which can act here. Okay, so this expression then I can write, let me write integration dp 2 pi h cut root over no, not root over, there are both factors, one factor from here, one factor when this come out, when it replaced by its eigenvalues, this is not a operator, it will come out, then you will have this inner product. So 2 inner product root 2 pi h and e to the power minus I h part p x minus x prime. Okay, and h now xp. Now this is the simple classical variables xp, because it is already replaced by its eigenvalues. Okay, because you already know when this momentum, any momentum, suppose p operator acting on p state, it can be write p square value time p state, right? So by definition, so this will be like this if you consider in the normal ordering, but we are interested to consider it in the while ordering, because that is better. We feel that it is better because it is keeping the all option, and the same calculation if we do in the while ordering, it will be x p h while ordering, which x p operators, and x, this expression will be dp 2 pi h cut. Maybe we can prove this, I by h p x minus x prime times h will be x plus x prime by 2 and p. So notice everything is same except this changes. The Hamiltonian will change it to eigenvalues, but its position eigenvalues were taken in two places, x and x prime, and divided by 2. Momentum, of course, it is. And this comes in the while ordering. So if we have a Hamiltonian in while ordering, then it is the Hamiltonian has to be in the midpoint. So this is called midpoint prescription. Okay. So this midpoint prescription, mm, this midpoint prescription will be using. But how to prove this? I can prove, but it will take little bit time. But let us prove this. So how you consider while ordering for a because it gives some two important concept in this proof. So let me go through the proof. So in general, for that, first we'll assume that any Hamiltonian is function of x operator and p operator. we can think of a most general Hamiltonian. Most general Hamiltonian can be some constant alpha times x, beta times p to the power n. Hamiltonian will have, so this in general, it can have a binomial expansion, all possible power of x and p up to n in your choice. For example, if it is a harmonic oscillator, you have x square term and p square term. If you have a linear term, then p square term and this. So most general Hamiltonian can be of this form. So if we know how to handle this, then we know how to handle this. A Hamiltonian cannot be go beyond this. Of course, exponential and other possibilities are there, but exponential always you can write in terms of linear terms and this. So basically, if we know how to handle this term in normal ordering. So I am going to write a expression for this binomial expansion, which you should prove yourself or verify yourself. N and m sum over n of n to sum such that n plus m equal to capital N. This you must be familiar in binomial expansion. N factorial, m factorial, and alpha to the power n, beta to the power m, and then x to the power n, operator x to the power n, operator p to the power m of while ordering. So this quantity can be written in this as a while ordering of x to the power n Pn. So this this means that you can so prove this. So first thing is that verify this for n equal to 2 and 3. So first verify this result for n equal to 2 and 3. 2 is very simple, 3 you will need little bit of calculation, but now let us calculate, assume that what will happen if this quantity's expectation value x prime alpha x e to the power, let me write e to the power alpha x plus beta p x prime. In this quantity we calculate in while ordering. So if we know how to calculate this, I can use the same result to find for any Hamiltonian. This is the idea. So this gives all kind of while ordering monomials in while ordering, and then if you have a term, this is for convenience we write, and then we can find that whether this quantity how you will behave. So here one important concept which you need to solve many problems that will be using. So e to the power alpha x plus beta p can be written as e to the power alpha x by 2, e to the power beta p, e to the power alpha x by 2. This is funny, but you know there is a formula that when you have some operators in the operators which is not commuting, e to the power b, where they are commuting operators, then e to the power a plus b, when a b commutator is 0. But if a b commutator is not 0, then you need Baker-Hausdorff formula. So that formula is right hand side, e to the power a plus b plus commutator of a b, and there is a series of infinite series depending on how that. So this formula is useful to solve many operator problems in quantum mechanics, which is also asked in NET, JEST, GATE exams. So Baker-Hausdorff formula, that people generally do the mistake, the e to the power a, e to the power b is not e to the power ab. So that you can verify here, that proves this using Baker-Hausdorff. So you can prove this is very straightforward, one or two line proof. I'll be using here this expression. So my expectation, this matrix element, I can calculate alpha x by 2 e to the power beta p, and then e to the power alpha x by 2, and then I'll have x. Now I have what happened, this important thing is that I have x here which can act on this, I have x here which can act in this, such that I can replace their eigen values. Okay. And now in this we have to put the so this I can write that momentum space inner completeness relation x prime e to the power alpha x by 2. This and this is fine, but what about p? So p we have to can deal by putting the momentum space completeness relation. Or operator. So this I put, this I can put, this is 1, but now this operator, which is only a p operator, can act on the p states. So I can find everything's eigenvalues, right? So this will be now dp, and then this this when acts on this, we can write e to the power alpha x prime by 2, and this is now not an operator, it acts, so it's replaceable. This when acts, it will be beta now p eigenvalues, and when this acts on that, it will be alpha x by 2. All these are not operators, and then you have x prime p and p of x. So what you will have now see, this is has become x prime, this is, so this you can dif p, so you will have e to the power alpha x prime plus x by 2 plus beta p, and these factors will give you minus I by h p x prime minus x and 2 pi h cut. So immediately I can so let me, I think I have written. So immediately I can write, if a general quantity like e to the power alpha x plus beta p can be written in this, I can write my Hamiltonian. If I my Hamiltonian in while ordering, I can write this. So this is the proof of the midpoint prescription that you will have. So I can write immediately x prime h while ordering xp x will be integration dp 2 pi h cut e to the power minus I by h cut p x minus x prime. H will be now x plus x prime by 2, because this you can see the midpoint prescription times p. So instead of the exponential, I just replace the a Hamiltonian, because this is a most general function, so it is true for most general function, so it will be true for the Hamiltonian. So this is the idea. Okay, any question on this? Okay, now we have all mathematical tools for calculating the path integral amplitude. Okay, the amplitude for some initial time to final time. So now we are going to let us use a different pencil. We want to calculate u some t final, x final, and t initial, x initial. This quantity now we can calculate. So this is the amplitude from this point to this point. Particle is created here. What is the probability of finding amplitude of finding that particle in this point? That t xf final point is given by this. Now we are going to calculate this. Now to calculate this, this is a finite time, so we need to break this time interval, final time minus initial time, into a number of pieces, because we want to go. So suppose this is your time interval, this is t initial, this is your t final, so we can break into small slices, such that we can go from one step is just an infinite decimal time. So very small. So let us define my epsilon, which is a small infinitesimal time, is tf minus tn, and at the end time is my continuous, time is continuous, right? So at the end we'll take n going to infinity limit such that epsilon will go to 0. So this limit will be taken at the end after calculating this quantity. And also in our notation, let me write Tn, nth slice time will be T initial plus n time epsilon, right? T initial, this is the T initial, this is the T1, T2, T3, last but one will be Tn, and then you will have T final. Okay, Tn minus 1, and then you will have T final. Okay, n intervals are there, so the total number of points will be n plus 1, because n interval n plus 1 points will be there. Okay, so any time t we can have. So now by definition, this our u, let me write in short, but okay, let me one times I'll write xf, then ti xi will be then I can have this Heisenberg picture Tf xf Ti xi h. Okay. So this is that, but now I'll break into the n intervals. So this u then now can be written as, let me write t. So how I can break it? I can break it by putting the completeness relation for the position. So dx x x equal to 1 unit. So that I will insert every point, and we can find that of course that will insert in the Heisenberg picture. Which we can calculate, will be n such inner, which we can calculate, will be n such inner product, which we can calculate. One we can calculate and then can multiply. Okay, so this let me write. There will be some integration. So here Tf xf, then I insert T n minus 1, last second last interval, the T n minus 1 x n minus 1 and T Heisenberg picture T n minus 1 x n minus 1. This completeness relation I can put and of the x n minus 1. Okay, dot dot dot, because now I can put another dx n minus 2. I can put another here t n minus 2 x n minus 2 times t n minus 2 x n minus 2, another inner product, another integration, and the last term will be let me write, you can understand. Last term, let me write, last term was t initial and x initial. So before that you will have t1 x1 and t1 x1, and the last integration will be d of x1. So what I did, I n minus 1 completeness relation I inserted, and now I have the inner product all in the Heisenberg picture, or I have an inner product of this kind which I can calculate. So how many inner products, such inner product will be there?
n
N number of inner product, because it is starting from in x initial. So 1 is not the last one. Last one is the, so n plus 1 such point is there. So there will be n such inner product. N such inner product. But notice there are integration over n minus 1 variable, 1 to x n minus 1. So this difference you should note. So n such inner product. Now I will show you how to calculate this inner product for one case. Suppose the nth, small nth inner product. I'll show you how to calculate. Calculation is very simple, only Gaussian integration is needed, but you have to you should know what is the Gaussian integration. So nth inner product, that means Tn xn into Tn minus 1 xn minus 1. How to calculate this? So this I can now, to calculate this, also remember one thing which I didn't write, but according to my notation it is clear. T final is the highest letter time, so it is greater than Tn minus 1, Tn minus 1 greater than Tn minus 2 dot greater than T1 is greater than T initial. So there is already a time ordering is there, T final to T1. So this is important. So this inner product are because of that. Okay. And let us first you know how to calculate this, then I can product the n times and then we can find this result. We have to find, this is the quantity we are finding, and that is everything. That is the only thing you have to calculate in path integral formulation. So we are process of deriving that path integral result. So how this quantity now this is in Heisenberg. Remember, all these are in Heisenberg. I forgot to write, but everywhere there is a Heisenberg. Okay, now I go back to the for this calculation I'll go back to the Schrodinger picture. So I can write xn. Now xn, when I write xn, it is implied Schrodinger picture, or if you want you can write xn, and it will be e to the power minus I by h cut Tn h. Okay, and from this side you will get e to the power minus I h cut. No, this side you will get plus. This is actually in the brass space, so I bring into ket space, so it is minus I h cut Tn minus 1 of h, and then x n minus 1. Okay, is that clear? I'm just using the basis vectors relation between Schrodinger picture and Heisenberg picture. So let me write S, but whenever I write only x variable, it is notation is that it is Schrodinger picture. But for Heisenberg picture, I am supposed to write H. Okay, so this I can write okay, x and s, and then this if I combine e to the power minus I h cut Tn minus Tn minus 1, Tn minus Tn minus 1, one of the smallest time interval, which is by definition is epsilon, right? Because I divide for by n and then we define epsilon, so epsilon times h. Here see, this first h is at time Tn, second h is at time n minus 1, and we are assuming Tn to Tn minus 1 is infinitesimally close and Hamiltonians are not changing. So that is the reason I break into the smaller pieces. So h is not changing, or it's same in this infinitesimal time change. Okay, so this is x minus 1 Schrodinger. So let me omit Schrodinger now. Okay, so this is the quantity you have to calculate. Okay, and we will calculate this in the using while ordering. So this is the quantity, you know how to calculate while ordering, that it should be midpoint prescription. So if I use the formula for while ordering that I derived today, this formula, so if I use this formula for this calculation of this inner product, so I can write dPn 2 pi h cut and then I will have this will be replaced by the xn and xn plus 1. So e to the power minus I by h cut epsilon h will be replaced by xn plus xn minus 1 by 2 and pn. Okay, and then I will have xn xn minus 1 inner product, which no, this will have sorry, this you have to do by putting the completeness relation, which we have done in this formula. So I'll be using this directly, this factor. So this factor will be directly I'll be writing. So e to the power minus I by h cut pn xn xn minus 1. Okay, x prime, let us see the formula again. X minus x prime minus or plus. Okay, so this you will get this. Let me check. Is that fine? IPN. I think this will be plus. See. See where x prime, then minus x prime. So x prime minus x will be plus. Okay. So this will be plus. Okay, so these are two exponential quantity. They are by number, so I can write. Let me write dpn. This is a very important derivation in path integral approach. So hn, which is xn plus xn minus 1 by 2 and pn, and then I write ih cut pn xn minus xn minus 1. Okay, so this is the result of. So this is so now this is the only one nth inner product, nth inner product. So now what will be my u? Okay, remember u has integration x1 to xn minus 1. Now for each inner product there will be a p integration. How many p integration? dp1 2 pi h cut dot to dpn. Here it is n minus 1, it is n 2 pi h cut, and then I have to product of all this. So product means, let me write, so it will be sum e to the power sum over n 1 to capital N epsilon h ih cut minus ih cut, let me write epsilon, so xn plus xn minus 1 by 2 pn, and then there will be minus pn, because minus ih cut I have taken common, xn minus xn minus 1. Okay, so this is my u. So now I have through to my u, only we need to simplify. So this is our u, and as I promise, I should take the continuous limit. Continuous limit means capital N going to infinity or epsilon going to 0. That means time will be continuous. So this is my u, and now you have to see that you have to perform this calculation, and you can you can perform this p integration. So let me write this compactly, this as d of x, compactly as this is d of p, and then then you will have u equal to this e to the power, I can write compactly, and then pn okay, so e to the power minus I by h cut minus I by h cut, or if I write plus, then better to write plus, because I'll write first term So it will be an epsilon, let us take outside epsilon, then first term will be this, I am writing plus, so this first term this is plus, so I'll write Pn xn minus xn minus 1 by epsilon, because I have taken epsilon common, there is no epsilon here, there is epsilon, and minus h xn plus xn minus 1 by 2 and Pn. Remember, we have the limit epsilon going to 0 and going to infinity. Now immediately you can see this. So let me write this integration compactly, and then so this I can write in this continuous limit I by h cart integration dt. This epsilon is like a dt, and epsilon is dt, then it can be written as p x dot time derivative of this limit epsilon going to 0, this is derivative xn minus x, so px dot minus h. And when epsilon going to 0, xn and xn minus 1 will be same, right? Epsilon going to, they are differ by only epsilon time, so this they will be same and they will be again. So this now what is this quantity? This quantity, if you know a little bit of classical mechanics, is nothing but your Lagrangian. So you have dx dp e to the power I h cart times action. So this is your u, the amplitude in path integral. Why it is called path integral, that will come with the argument, but let us first find this formula. This px dot minus h is nothing, is your L, right? This is your L, okay, because you know h equal to px dot minus L, so that okay. So this action is nothing but L dt, so initial time to final time, okay. So this is your Ti to Tf. So path integral amplitude now we have calculated, and it is written like this formula, okay. So but one thing we can do, the momentum integration, if you look at your for example, if you have a non-relativistic system. Non-relativistic system is basically p square by 2m times v, right? Now if I write your h as p square by 2m and there is a p here, so this is basically a quadratic integration. For non-relativistic quantum mechanics, p integrations is simple and can be calculated. Simple and can be calculated. So but this is just a Gaussian integration. This p integration will be like minus infinity to plus infinity e to the power ax square plus bx kind of integration dx. This integration you have done. This is gamma function integration and you have done. So p integration, you have a linear term in p, you have a h has a p square term. So x square and linear term. So these two terms are there. So this p integration can be calculated, and I'll show how to calculate the p integration. And then this formula can be written in a further simplified way. So but major part we have done. This path integral formulation can be now I'm going to show you for non-relativistic quantum mechanics, if your Hamiltonian is p square by 2m and v has no p dependence, so I can, if in this form, you can find the calculation. So let us we have 10 minutes, so we'll do this calculation, then we'll stop. So this is basically to show you. So for that, we just again go back to the nth inner product. So this was the nth inner product, e to the power minus I h cut epsilon, and h I'll write now. H is now Pn square by 2m minus Pn xn minus xn minus 1 by epsilon, and there will be a v x n plus x n minus 1 by 2, assuming that it is only function of v. So it is the Hamiltonian, so the plus sign, and this will be minus sign that we have. So now let us perform. This will not matter, so it keep as it is. Only p dependent terms are there. So I can make a perfect square. If you, so let us take, I am taking all this thing common, e to the power minus I by h cut epsilon. Now take 1 over 2m common. So common. So it will be Pn square minus 2m times Pn xn minus xn minus 1 by epsilon. This outside, let it be outside because integration does not matter. So, okay. So this I'll come back when I'm performing this integration. We'll write this term. Okay. So e to the power minus I h cut epsilon by 2m. This now this I can write Pn minus 2 times Pn. So m xn minus xn minus 1 by epsilon whole square. I can make a perfect square, and I have to substitute this term m square x. I have to subtract this term epsilon square. Okay. So what is the remaining term? This is the integration, and that what will be the result of this integration, that I'll tell you. But before that, let me get back to this term. So this term is minus I h cut epsilon by 2m, then m square epsilon square xn minus x, let me write here n minus 1 epsilon whole square, this epsilon. So this term is basically e to the power minus I by h cut. Epsilon will be of course there. M will get cancelled. So 2 and then m. 1m will get cancelled to that. Okay. I h cut epsilon m, then xn minus xn minus 1 by epsilon whole square. So this is also outside the integration because this is no p dependent. So this term is outside. This term with this factor will be outside. Now we have remaining with dPn. Forget about other factors. E to the power minus I h cut epsilon 2m Pn minus m xn minus xn minus 1 by epsilon this whole square. Okay. This is nothing but, and this all momentum are minus infinity to plus infinity. So if you have a integration, okay, this I can write, I can shift my p to this. This is a constant with respect to p. So this I can have further this simplify this integration dPn prime, say, by substituting h cut epsilon by 2m Pn prime whole square. So my Pn prime is Pn minus m xn minus xn minus 1 by epsilon. Okay. So I substitute now this. Okay. So this integration now compare with minus infinity to plus infinity x e to the power a minus a x square dx. And result of this integration you must have done many times is root pi by a. Minus a x square, this integration is pi. If you have not done, please verify this. What is my a here? A is this quantity. So what is the result of this p integration? Root pi, then a. A is I epsilon, okay, and then pi by a. So it is I epsilon and then 2m h cut. And remember, I have a factor of 1 over 2 pi h cut, right, in this factor. You remember this factor Pn by this factor. So this factor also I'll combine with this. So if I bring into inside the square, it will be pi 2m h cut, and this will be I epsilon times 2 pi h cut times 2 pi h cut, because this one is now pi 2 pi h cut will get cancelled. So this factor will be m by 2 pi I epsilon h cut to the power half. So basically, so this you have to do the
Sir.
calculation. Tell me. Hello.
Sir, here is many times I will we will put the 1 upon 2 pi h cut.
Hmm.
Can I simplify it and we will direct like to write 1 upon h?
Yeah, that those things. But first, you should know that what is the amplitude. Calculation you should write once. Now you can take your m to be 1, h cut to be 1, 2 pi h cut to be 1. Those are the convention. If you when you calculate a number, then you will not get the factor unless you see velocity of light you can put equal to 1. But when you want to calculate a number, some how much mass changes, then you have to put the actual value. So I am doing, but that this calculation you should do once. This is, after that we'll forget about. So for the nth inner product, we get a term factor of m 2 pi I epsilon h cut to the power half, and you remember those factors are lying behind this factor, where this factor and the v factor. So you have to write those. So so you can write the these factors. So this here x by x x and minus, and there was a minus. I forgot there is a minus. There is a this minus and there is a this minus. So this term will be plus. You can check yourself. This minus and this outside minus. So the terms will be plus I h cut epsilon m by 2 h cut xn minus 1 by epsilon whole square. This is coming from the making the p as a perfect square, and there is a term remaining with the v term with the minus. So minus I epsilon, let me write. So minus I h cut epsilon v minus I h cut epsilon v minus I h cut epsilon v xn plus x. Okay, v xn plus xn minus 1 by 2. Now this is only nth product. So if you have a if you go back to all product of all this, your factor will be m by 2 pi I epsilon h cut to the power n by 2, because n such factor. So this, and this will be sum to the power I h cut sum over sum epsilon also outside, sum over n m by epsilon I. There is a why there is a, there don't be 2 h cut, no? This h cut will be not there. So let me write I epsilon m 2 h cut 2 h cut where from these two factors. Okay, xn minus 1 by epsilon whole square and minus I by h cut. So minus I by epsilon v xn plus xn minus 1 by 2. Okay. So now you take the epsilon going to 0, n going to infinity limit, and there is a sum. Remember, there is a sum now because all inner product. So sum will be n equal to 1 to n. So when we do this, we will get a exponential terms I by h cut. Then I'll get half m integration, it will be dt half m. This is nothing but xn minus x minus 1 by epsilon whole square. So it is x dot square, and this will be v of x and integration dt. Integration dt I have written. So again we get the Lagrangian half m x dot square minus vx. This is your Lagrangian. So we get e to the power I h cut s. So final u is now only x integration. P integration has been done. E to the power I h cut s. So this is your amplitude in path integral. Why it is path integral? What is the meaning of this formula? We'll discuss in next class. I just complete this derivation. You go through this derivation. Every step is very clear to me. I may be little bit in hurry towards the end, so you may have some confusion. So just uh, do this step. This is very important, and this is first time and last time was done to you by in a class. Nobody else will do in the class this derivation. Okay, so I'll stop here unless you have some question. Two things I want to say. That one is that I decided to take some classes on such that you can prepare your net gate, assuming that you will be that will be helpful to you and you will be attending my classes. But since you are preparing yourself, I think those are not meaningful, right? Classes, because only less than 50% student are attending. 9 student, 2 student came 20 minutes late. Bishwajit, Sonam, they came. They are not very casual. So if you people are not wanted to learn the class, then what is the point of seriously teaching? I can teach without being seriousness. I can give you this formula, just check in the book and find the derivation. But anyway, so I'll stop here. Let me stop recording. But this I want to say that people should attend the class even if they have the exam, because exam will be there in February. Exam will be just whole semester they will not attend the class. So this is a message to the all students, has to attend the classes. Unless if you don't attend, then there is no point of teaching, right? I have many other things to do.